In question 1a, we're given 3 boxes which show different arrangements of particles in different states, and we're asked to write under each box the state of matter shown. So we can see we've got 3 different states of matter. We can see this one is clearly a solid. The reason we know it's a solid is because it's arranged in a regular arrangement and the particles are close together. And we know this one over here is a liquid because the particles are close together, but it's not arranged in a regular arrangement. It's like a random arrangement because liquids, the particles are randomly placed around, whereas solids, they're in a regular arrangement. Over here we have a gas. We know this one is a gas because the particles are really far apart, and again because they're in a random arrangement. It's not a regular arrangement. So in this next question, the student is given some solid wax, and we have to use words from the box to name 2 pieces of equipment that the student should use to convert, that means change, the solid wax into a liquid. So we want to turn a solid into a liquid. So we need something that's going to heat up the solid to change it into a liquid. So a Bunsen burner would be a great choice to heat it up. And then we need something to put the solid in. So we need to find one of these things that we can put the solid in. Well, a test tube is a great thing that we can put something in. So we can put the solid wax into the test tube and then heat it up using the Bunsen burner. A burette is a piece of glassware, which can be made out of plastic, which is used to measure liquids. A pipette is the same thing, but used to measure in a slightly different way, but it's a glass piece of equipment used to measure liquids. And a filter funnel, well, that's used to filter out solids from liquids, so to remove the solid from some liquid. So these 3 wouldn't be very useful, but the Bunsen burner, the test tube would work. In question B, we're told that there's some liquid left in a warm room, and after a few days, no liquid can be seen. So we need to name the process that has occurred. So what is the name of the process when a liquid disappears? So it must be disappearing, it must be turning into something else. Liquids can't just disappear. So the process is called evaporation. Evaporation is the process of when you have liquid particles. So here's some liquid particles. They're all hanging around. And what happens if we have a warm environment, some of them gain enough energy, and they gain enough energy to break free of the liquid and turn into a gas. And over a long time, this can happen, and all of the liquid particles can turn into a gas, so we have no liquid left, evaporation. So in question 1c, it's telling us the freezing point of water is 0 degrees. Describe how the movement and arrangement of water particles changes when water is cooled from 10 Celsius to minus 10 Celsius. So we're going from 10 Celsius, which is above its freezing point. So if a substance is above its freezing point, then it is a liquid. And if a substance is below its freezing point, then it is a solid. And if it's at its freezing point, that's the point where it turns from a liquid into a solid. At 10 Celsius, the particles are going to be moving around faster, they're going to have more energy, and they're going to be slightly further apart. Or you could say the converse argument, so the opposite argument, which is at minus 10 Celsius, the particles are going to be slower, or pretty much not moving because they're in a solid, just vibrating. So they're going to have less energy, and they're going to be closer together and arranged in a regular arrangement. Whereas as in a water, they're going to be arranged in a random arrangement. Question CII says, what is the structure of water? So water is composed of hydrogen, oxygen and hydrogen. So it's H2O. And we draw these lines between them showing that there are covalent bonds. And hydrogen is a non-metal and oxygen is a non-metal. So when you have 2 non-metals bonded together, generally they're going to have covalent bonds. And generally if they have covalent bonds, they are a simple molecule. There's a few exceptions to this, things like diamond, graphite, graphene, which have and a few others that you don't really need to know. So in question 2, it asks you, it says that ammonium phosphate and ammonium sulfate are made from ammonia, and these compounds can be used as fertilizers. It tells you that ammonia solution is alkaline, and it says which of the following could be used to show that ammonia solution is alkaline. So something which tells you whether something is alkaline or acidic is a pH meter. A pH meter tells you how acidic or alkaline something is. If it has a pH of between 0 to 7 or less than 7, it's acidic, and higher than 7, it's alkaline. A conical flask is just a piece of glassware used to put liquid in. A pipette is a piece of glass or plasticware used to measure out liquids, and a thermometer is used to measure temperature. So question 2b says, give one advantage of using fertilizers made from ammonia rather than using manure. So manure is like animal poo. So the problem with using manure is that it's not that reliable. So these fertilizers made from ammonia are very reliable fertilizers. Manure depends on what the animals have eaten. Another good thing about ammonia fertilizers is ammonia is very soluble. So because it's soluble, that means it can dissolve in liquid, in water, and can get to the roots really, really easily. And another thing you could write is that ammonia, these fertilizers made from ammonia are really easy to produce, mass produce, so produce on large scale. So any one of those would be a good answer. So question 2c says the fertilizer ammonium phosphate was made by reacting ammonia solution with dilute phosphoric acid. In the first step, 25 cm cubed of dilute phosphoric acid was placed in a beaker. Give the name of a piece of an apparatus that could be used to measure out the 25 cm cubed dilute phosphoric acid. So we could use a measuring cylinder, or we could use a pipette, or we could use a burette, so any one of those. So question CII says complete the word equation for this reaction. So we've got ammonia, and we're told that what it produces. If you read up here, it says the fertilizer ammonium phosphate was made by reacting ammonia solution and phosphoric acid. So we know it's producing ammonium phosphate with ammonia plus phosphoric acid. So we need to have phosphoric acid here. So all this question required you to do was actually just read this and see what was made. So what was made goes on the right hand side of the arrow, and then you look at what was used to make it. So it says it used ammonia and phosphoric acid to make it. So those things go on the left hand side. They're the reactants, and that's the product. So this question reads that some ammonium phosphate solution was made, and it says describe how pure, dry crystals of ammonium phosphate are obtained from the ammonium phosphate solution. So how can we turn a solution into pure, dry crystals? Well, the first thing we need to do to turn a solution into a solid, a dry solid, is to heat it. So we heat the solution, and that will leave us with just some dry crystals. Alternatively, we could just leave the solution for the water to evaporate, or we could heat it and let some crystals form and then filter those crystals using a filter and a funnel. So this question says the formula of ammonium sulfate is NH4 brackets little 2 and then SO4. What is the empirical formula of ammonium sulfate? The empirical formula is this formula, but shown in its simplest whole number ratio. What that means is you look at the formula and see if you can divide it by a number, say 2 or 3, so that you've got a simpler ratio. For example, say you've got something like C2H4, this is ethene. We could divide 2 and 4, they both divide by 2, so we can get CH2. So over here is its molecular formula, how it actually looks, and this is its empirical formula, which is just its molecular formula, but in its simplest whole number ratio. You see there's no number here, that's just considered, if there's no number, to be a 1. So if we look at this, first we've got to expand the brackets and see how many different nitrogens and hydrogens we've got. Because if you have a little 2 to the right hand side of something in brackets, you have to multiply everything in the brackets by that number. So let's expand the brackets. So we get over here n1 times 2, so we've got 2n, so it's n2, and then we got h4 but times 2, so 4 times 2 is 8, so we've got 8 h's, and then s, because that's not in the bracket, so we don't times it by anything, and then O4 again, same reason. So we've got N2, H8, S, no number, so 1, and O4. So is there any number we could divide all of these by to give us a simpler whole number ratio? Well, the answer is no, we can't, because if we divide it by 2, if you divide sulfur, remember sulfur had a number here which is 1. I'll put that in actually. Let's put that in. So sulfur here is 1. You can actually write it. If we divide everything by 2, 1 divided by 2 is 0.5 or half. You're not allowed that. You have to have an empirical formula, has to be whole numbers. So therefore the empirical formula for ammonium sulfate is actually the same as its molecular formula, as we cannot divide it by any numbers. So therefore the answer is, whichever one is the same without the brackets, is C. So question 3. Unreactive metals are found as uncombined metals in the Earth's crust. Which of the following metals is found uncombined in the Earth's crust? So this, you have to know which is sort of the most unreactive metal. So aluminium is very reactive, so therefore is always found combined. Sodium is even more reactive, so is always found combined. And zinc, again, thinking about your reactivity series you learned, zinc's quite high up on that, it's quite reactive, so it's found combined with other elements. Gold, however, is very unreactive, so therefore is often found on its own, uncombined, so you can just find it in the ground. You can't find aluminium, sodium and zinc on their own as a metal in the ground. It's always combined with other elements, generally oxygen or chlorine, whereas gold, you can just find it, you can dig in the ground, you can actually find just solid gold. When the iron oxide is heated with carbon, so iron oxide is heated with carbon, iron is produced. So we know what's produced, iron is produced, that's the product, so that goes over here on the right hand side. Okay, so we've got iron. It tells us when iron oxide is heated with carbon, iron is produced. So, well, what's left over? We know that iron is produced here, which means we've also got carbon and oxygen left over. Remember, elements can't be destroyed, they can just be sort of recombined. So originally the oxide, that's oxygen, was combined with the iron, but now it must be combined with the carbon because there's only one space left. So what do we call something which has carbon and oxygen? Well, one possibility is carbon dioxide, which is the most likely. What happens to the iron oxide during this reaction? So we've got the iron oxide burns, the iron oxide is neutralized, the iron oxide is oxidized, or the iron oxide is reduced. Well, the iron oxide, you can see it's losing oxygen. So if something is losing oxygen, we say that it has been reduced. So reduction, reduced, is when oxygen is being lost. Oxidation is when oxygen is being gained. Neutralization is when you have an acid and an alkali reacting together, neutralizing each other. And burning is when you heat something up in oxygen generally. So C, copper ore contains copper carbonate. Copper carbonate, that's the CO3. In the first stage of the extraction process, that means we're trying to get copper on its own. The copper carbonate is decomposed. Decomposed means when you break something up by heating it to form copper oxide. So copper oxide there, CuO, and carbon dioxide. So we're trying to get copper, but the first step is to turn the copper carbonate into copper oxide. And then it says when 100 grams of copper carbonate is decomposed completely in this way, it is found that the total mass of the products is 100 grams. Give a reason why the starting mass of copper carbonate, that's the copper carbonate, is always the same as the mass of the products formed. So this is due to a law called the conservation of mass, which states that the mass will not change. We've still got the same number of atoms. If you count them, you can see you've got one copper atom. There's one copper atom on the left-hand side in the reactants, and one copper atom still in the products. You always get that. We've got one carbon atom in the reactants, and we've still got over here one carbon atom in the products. We had 3 oxygen atoms in the reactants, and you can see you've got one oxygen atom here in one of the products, 2 oxygen atoms in the other products, so it adds up to 3. So you can see you've got exactly the same number of atoms, therefore the mass will be exactly the same. And this is always the case for a reaction, the mass never changes. So we can say that no atoms have been created or destroyed, they've just simply been rearranged. They're no longer bonded to the same things that they were bonded to originally. So zinc can be extracted from its ore by electrolysis. So electrolysis is when you pass electricity through a solution or a molten liquid, and it causes things to separate. Lysis meaning separate. So we can extract zinc by electrolysis or by heating the ore with carbon. Give a reason for the method that is used. So we can heat stuff and extract stuff with carbon if carbon is more reactive than the metal that we want. Now, if you remember your reactivity series, you'll see that zinc is less reactive than carbon. Because it's less reactive than carbon, we can use this method. And this method is a lot cheaper and a lot quicker and easier than electrolysis. If the metal was more reactive than carbon, we'd have to use electrolysis, but we don't want to because it's quite an expensive process. So figure 2 gives information about aluminium and tin. So you can see aluminium, the cost of 1 kilogram is £1.51, and there's about 8% in the Earth's crust. So it's quite a lot in the Earth's crust. Whereas tin, the cost for 1 kilogram is a lot more expensive. It's £12.60 for 1 kilo, and there's a lot less of it in the Earth's crust. So it says give 2 reasons why it could be more important to recycle tin than to recycle aluminium. And we have to use the information in figure 2. So the first one we could use is the cost. So we can see how tin is much more expensive. Therefore, because it's more expensive, it might make more sense to recycle it. It's actually almost 10 times more expensive. Another reason we might want to recycle tin more than aluminium is due to the amount in the Earth's crust. We can see that there's quite a lot of aluminium in the Earth's crust, but hardly any tin in the Earth's crust. Therefore, once we've used it up, it's gone, so it's better to recycle. So question 4 reads that an electrolysis experiment is carried out on different solutions, J, K and L. Electricity is passed through each solution as shown in figure 3. So you can see electricity coming from here, passed through the solutions. So we can see the products formed at the electrodes are identified. So the cathode is our negative electrode, so we can see what's formed there, and our positive electrode at the anode, we can see what's formed here. So, first question, state an improvement that can be made to the circuit to show that a current is flowing during electrolysis. So what measures a current? What piece of equipment can we use to measure a current? Well, an ammeter is a piece of equipment which we can use. We can attach it in series, and we can use to prove that a current is flowing because an ammeter measures current. In series just means that it's connected, the wires are connected directly to the ammeter, which is different to a voltmeter, which is connected in parallel. The next question reads, it says that some of these solutions are electrolytes. State what is meant by the term electrolyte. An electrolyte is a substance which conducts electricity when it's in solution or in a molten state. And molten just means liquid. So if you have a metal, a solid metal, and you heat it up until it turns into a liquid, that is its molten state. Question AAII reads, which of J, K, L are electrolytes? So I've copied figure 4 from the previous page. So we're looking for electrolytes. So which of these conduct electricity? Well, we can see that J conducts electricity and L conducts electricity, but K doesn't. Therefore, J and L are electrolytes. Question B says the copper sulfate solution was electrolyzed. for 5 minutes using copper electrodes. Figure 5 shows the mass of the anode and of the cathode before electrolysis and after electrolysis. So we can see that the mass of the anode has gone down. So before it was 1.16 and it's gone down to 0.85. And the cathode, the mass of the cathode is increased. And it says calculate the mass of copper deposited. So deposited means like left on. So this one, the anode, the copper has actually been removed. For the cathode, you can see the mass has increased. So therefore, copper must have been deposited, must have been left on. So we need to calculate how much copper has been deposited. So how much has been added. So we need to find a difference. So if we look at the difference, if we take 1.57, that's how much we had at the end, minus how much we had at the beginning, 1.28, and we work that out, we should get a difference which equals 0.29. So we can see the difference between 1.28 and 1.57 is 0.29, so therefore 0.29 grams of copper have been deposited. So it says in a different electrolysis, molten sodium fluoride, there's the sodium fluoride, is decomposed. Remember, decomposed means broken down. You can see it's broken down into sodium and fluorine gas. It gives us the relative atomic mass of the fluorine and the sodium. It tells us the relative formula mass, that's the sort of formula mass of the whole thing, sodium fluoride. And it asks us to calculate the maximum mass of sodium that could be formed from 168 grams of sodium fluoride. So we can see that we've got 2 sodium fluorides. See the big number 2 there? So each sodium fluoride has a mass of 42. So if we have 2, that's 2 times 42, which is 84. So we've got 84 grams or mass of sodium fluoride, and that's going to make 2 sodiums. Each sodium has a mass of 23. So again, 23 times 2 is 46. So 84 mass of sodium fluorides makes 46 mass of sodium. And then it says calculate the maximum mass that could be formed from 168. Well, 168, we can see how many times bigger is that than 84. So how do we get from there to there? Well, you can see it's 2 times bigger. So if we have double the amount of sodium fluoride, how much sodium is it going to make? Well, it's going to make double the amount as well, 2 times. So 2 times 46 is 92. So therefore, 92 grams of sodium are produced. Now, this method is one way you can use to work out this question, but it's not the method I'd use. I do something else which involves working out moles, which you may or may not have heard about, but I'll show you how to do it because it makes a bit more sense. So for questions like this, what we generally do in chemistry is we work out a thing called the moles. Don't really worry too much about what that is. What we do is we take the mass, 168, and we divide it by its relative formula mass, so 42. And that will give us something called the moles. So 168 divided by 42 equals 4. So we've got 4 moles of the sodium fluoride. And now we want to work out what is the mass that 4 moles of sodium fluoride will make. How many moles, how many grams of sodium will it make? Well, we can see the ratio that for every 2 sodium fluorides, we make 2 fluorines. So if we have 4 moles of sodium fluoride, we're going to make 4 moles of sodium. So we've got 4 moles of sodium being produced. That's of sodium. Okay. To work out the mass of sodium, so the mass of sodium is just the moles times its relative atomic mass. So we got 4 moles times the relative atomic mass, which was over here, 23, so times 23, so 4 times 23 equals 92 grams. If you're interested, the sort of equation which I was using there is this. It is moles times relative atomic mass, or AR, equals mass. We could rearrange that equation any way we want, so therefore moles equals mass divided by relative atomic mass. Again, this might be a bit beyond what you need to know, but it's very useful for working out these sort of questions. If you're really confused by this type of question to do with moles, and you really want to know more about using these equations, I've done quite a few other videos on this, but there's no point in me going into it here because it's quite a lot in depth, so just check out one of the other videos. So question 5 reads, gives 2 advantage of electroplating metal objects. So electroplating is when we attach electricity to the object, and then we use, sort of like electrolysis, we use this to coat the object with another type of metal. So we do this for 2 reasons. The advantage is to improve the appearance. So we might have a copper coin and we can electroplate it with gold, so we cover it with gold so it looks like a gold coin. Good for metals. And we could also electroplate something which corrodes very easily. So say you've got some iron undergoes corrosion, it rusts very easily, so we could electroplate it with a metal which doesn't rust so easily. So in this next question it says solder. Solder is an alloy of tin and lead. So solder is something that we use, we heat it up and we can use it to like sort of connect stuff together. It's like a soft metal we use to connect maybe broken wires together. So a sample of solder was made by mixing 2.25 grams of lead with 15 grams of tin. Calculate the percentage of tin in this solder. So to calculate the percentage by mass, the amount of mass of tin in this case, but this works for any of these questions where it says calculate the percentage of a substance in a sort of total compound substance. So the percentage by mass of tin would be the mass of the tin, the mass of the metal, so the mass of the tin, 15 grams, divided by the total mass times by 100. So let's do that. So if we put the equal sign directly underneath, as we should with mass, so mass of metal is 15 grams, that's the mass of the tin, divided by the total mass, so that's 15 plus 22.5, that comes out as 37.5, so 15 divided by 37.5 times by 100. So throw that into your calculator, and that comes out as 40.0%. So 5C says the rusting of an iron nail was investigated by setting up 3 test tubes as shown in figure 6. So we've got test tube A, which just says water, test tube B, boiled water covered with oil, and test tube C, no water and a drying agent. State and justify the results you would see in each test tube after 1 week. So a drying agent, just in case you don't know, is something which sort of soaks up all moisture, removes all water. So the question's asking us what's going to happen in each one in relation to how rusted, if it's going to rust. So in the first one we've got water, and we've also got air. Now air contains oxygen, so we've got oxygen and water, and that's what you need to rust. So A will rust. So we can see B has water and has oil covering the water, so no oxygen can get to the water. So all the nail is surrounded by is water, but there's no oxygen, so it won't rust. And over here in C, there's lots of oxygen in the air around the nail, but there's no water because all the water is being sort of going into the drying agent, so there's no water. So that again, C won't rust. An iron bucket is coated in zinc. Over many years of use, the iron bucket has been scratched and left outside in the rain. Although some of the zinc coating has been removed to expose iron, the iron bucket has not rusted. Explain why the iron has not yet rusted. So zinc is more reactive. You remember your reactivity series. Zinc is more reactive than iron. So therefore, the zinc will start to react with the oxygen and the water will start to rust before the iron. So the zinc is going to corrode before the iron. You can sort of think of it as if they're both competing for the oxygen and for the water, and the zinc, because it's more reactive, he wins the competition, therefore the zinc corrodes first. So question 6 starts off by talking about the apparatus shown in figure 7 shows a piece of magnesium, there's the magnesium ribbon, being heated. During the heating, the magnesium reacts with oxygen from the air. The lid of the crucible, that's the crucible there, is raised slightly from time to time. Magnesium oxide was formed as a white powder. The experiment was repeated with different masses of magnesium. The results are shown in figure 8. So we can see there's 6 different experiments, and they use different masses of magnesium, starting from 0.1 going all the way to 0.5. And they recorded how much mass of magnesium oxide was formed in each experiment. So you can see how much mass of magnesium oxide was formed, the most being over here. And then they calculated the mass of oxygen in magnesium oxide. So you can see the mass of magnesium was 0.1, and it's increased to 0.16. Well, there's no magnesium being added. The only thing that's added to the magnesium is oxygen, so that extra mass must be due to the oxygen. So you can see how they've calculated it. They've just taken 0.16 minus 0.1 gives you 0.06. So if you take the amount formed, 0.8 in this example over here, you minus the amount you had originally, 0.5, it gives you 0.3, the amount of oxygen that must have been added to the magnesium to form the magnesium oxide. Now we're asked to draw a graph of the mass of oxygen in magnesium oxide against the mass of magnesium used. So we want the mass of oxygen in magnesium oxide, that's going to be on our y-axis, and we want the mass of magnesium used on our x-axis. So whenever drawing a graph, the thing is we've got to come up with a suitable scale. So if we can see that the mass of magnesium goes from 0.1 to 0.5, so we need to be able to reach 0.5. So say we start here with 0.1, 2, 3, 4, 5. So we can have here 0.5 over here. And we can see for the mass of oxygen and magnesium, it's going from 0.06 to 0.3. So we could have again 0.1 here, 0.2, 0.3. Now we just have to plot the data onto the graph. Just be aware when plotting the data onto the graph, the examiner will know if you've rushed it and made mistakes, and you will lose a mark here. You do have to plot it exactly accurate. Don't think, oh, he won't check. They will check each point, and it has to be very, very accurate for you to gain the mark. It's a very easy mark, so don't throw it away. So when you're choosing your scale, that's the number that you're going up here, so I've gone up by 0.1, 0.1, it must mean that the points that you plot cover at least half the graph. And that's measured by your bottom point. If I was to draw, say, a rectangle from my bottom point, let's use a thinner pen, from my bottom point here to my top point. So that's the area of the graph I've actually used. So even though my scale extends down here, I haven't actually used that area. So the examiner, when he's working out my marks, he looks at this area and he sees, is that at least half the graph? And you can see that is half the graph, that area I've used. If you did a smaller scale and your points were, say, just all in these 4 squares here, you would actually lose that mark. The second mark is that all of your points that you've plotted must be within 1/2 a square correct. So you can see if they will check each of these points, and if they are half a square out of place, in the wrong place, you will lose that mark. And the final mark is for drawing a line of best fit, and you can see this one very clearly is an anomaly, so we will actually ignore that when we draw our line of best fit. So here you can see my line of best fit. I've missed out the anomaly. I've actually included going through the origin, because if you think about it, if you started off with 0 magnesium, how much oxygen would be added? Well, also 0, therefore there is also technically a point at the origin, so that's why I've gone through the origin, although that's not actually important for this mark. Okay, the question then goes on to say the results for experiment 5 is anomalous, it's an anomaly. The masses were all measured accurately. Suggest a reason for this anomalous result. So what happened here? What suggests a reason? So this one, you'd expect this one to, the mass of oxygen added should be up here. So what's happened? Well, maybe the reaction hasn't finished yet. So maybe we didn't heat the magnesium long enough for it to fully react with the oxygen. Or perhaps maybe some of the magnesium was lost, or the magnesium oxide was lost. Perhaps if you, when you're moving the crucible to the scales, you accidentally spilt some of it. So any one of those reasons would be accepted. In part B, it says balance the equation for the reaction of magnesium with oxygen to form magnesium oxide. Okay, let's zoom in here a little bit. Right, okay. So we can see we have got on the left-hand side, so we're looking at, we draw a line down here. On the left-hand side, we've got some magnesium and some oxygen. On the right-hand side, obviously, we're also going to have magnesium and oxygen. On the left-hand side, I've got one magnesium and two oxygens, and over here I've got one magnesium and one oxygen. Now for balancing equations, we're only allowed to times stuff, and we're not allowed to divide. So we want to get another oxygen. So what we could do is we could put a big number 2 here, and that's going to mean we're now going to have 2 oxygens here, but it's also going to change the magnesium to 2 as well. So we've sorted oxygen. We've got 2 oxygens on the left-hand side and 2 oxygens on the right-hand side. But we've now got 2 magnesiums on the right, but only 1 magnesium on the left. So if we put a big 2 here, we've now got 2 magnesiums, 2 oxygens, everything's balanced, and we'll leave this one blank, or you could put in the number 1. So if you leave it blank, it's the same as putting in number 1. Generally, I would just leave it blank, but if it makes you feel better, you can put number 1 in there. Now I said that we aren't really meant to divide, but you can you are allowed to use halves. So think, how could you use a half to make that balanced? Well, if we put a half here, we've now got 1 magnesium, 1 oxygen, 1 magnesium, 1 oxygen on the other side, so therefore it's balanced. Now generally, normal equations don't use halves. You want to have full numbers. The only time actually really in real chemistry, in sort of A-level and university chemistry, we use halves is when we are dealing with things to do with thermodynamics, and we have to fit certain definitions, but generally we'll sort of want to avoid using halves and use full numbers. So part C says calcium nitrate contains calcium ions and nitrate ions. Remember, ions are charged particles, so a plus or minus charge. And it says calculate the relative formula mass of calcium nitrate. There's our calcium nitrate. So relative formula mass is simply worked out by adding up all of the relative atomic masses of the compound. So we can see we've got 1 calcium, so one calcium, which is 40, is a relative atomic mass of 40, plus how many nitrogens can you see there? Well, there's 1 nitrogen in the bracket, but remember, when you have a little number outside of the bracket, that little number multiplies everything inside the bracket. So we have 1 nitrogen inside the bracket multiplied by 2, so that's 2 nitrogens. So that's 2 nitrogens. Each nitrogen we can see is 14. So each nitrogen is 14, so 2 times 14. Plus the oxygen. Well, how many oxygens we've got? We've got 3 oxygens inside the bracket, but remember we have to multiply it by whatever is outside the bracket on the right-hand side, the small number. So 2 times 3 is 6. So we've got plus 6 oxygens, and each oxygen has a relative atomic mass of 16, so that's 6 times 16. So we throw that into our calculator, and we get 164. So question D says 2 oxides of lead, R and S, were analysed. The empirical formula of oxide R was found to be lead oxide, so 1 lead, 1 oxygen. The results of the analysis of oxide S showed that it contained 0.207 of lead grams combined with 0.03 grams of oxygen. Show by calculation that the 2 oxides had different empirical formulae. And it gives us the relative atomic mass of oxygen and lead. So what we want to do is we want to work out the empirical formula of S. So we've got lead on the left-hand side, Pb, and oxygen on the right-hand side, O. And what you do is you take the masses and you divide them by the relative atomic mass. And that gives you something called the moles. Again, you don't really need to know what moles are, but the number that it gives you, you compare those 2 numbers, and they give you the ratio of how many leads there are compared to how many oxygens. So let's do it. So the equation we're actually using is up here, that moles equals mass over AR. So we got the mass of lead, 0.207, that's the mass of the lead, divided by its AR, 207, and that equals 0.001. And then we do the same for the other side for the oxygen. So the oxygen was 0.032 grams divided by 16. And that equals 0.002. Okay, so we got 0.001 over here and 0.002 over here. And what you then do is you divide both of these numbers by the smallest number. So which one's the smallest? Well, this one's here the smallest. So we divide it by itself, 0.001. And we divide this one by the same amount, 0.001. You always divide them by the same number, the smallest number. So 0.001 divided by 0.001 equals 1. And 0.002 divided by 0.001 equals 2. And that's the whole number ratio. So you have 1 lead to 2 oxygens. So the empirical formula will be PbO2. So we've now proved that it's different to the other oxide of lead, R. The other oxide was 1 lead and 1 oxygen, whereas S, this oxide of lead, is 1 lead and 2 oxygens. This question says substances can be pure or they can be mixtures. Which of these substances is a mixture? So chlorine, that's just a gas, that's a pure gas. Sodium is a metal, pure metal. Sodium chloride is a compound, it's a pure compound of sodium chloride, like table salt. Sodium chloride solution, however, well, it's pure sodium chloride, and solution means with water, so pure water, but when you have the two pure substances mixed together, you get a mixture. So sodium chloride mixed with water is a mixture. So in question B it says, figure 9 shows some mixtures to be separated and possible methods of separation. Place a tick in one box in each row of the table to show the best method to separate the first named substance from each of the mixtures. So we've got to separate sand. We've got to separate it from a mixture of sand and sodium chloride solution. Now we should know that sodium chloride, table salt, is soluble. That means it dissolves in solution, and sand is insoluble. So therefore we can just use filtration. So we get a filter, a funnel, looks like that, and put some filter paper in here. We pour the mixture through. The sodium chloride solution and the water will go straight through, and we'll get sand collected on the filter paper, so we've separated them. So the next one says we want to get copper sulfate crystals from copper sulfate solution. Actually, there was a question very similar to this earlier on in this paper. So how can we get dry crystals from a solution? Well, what we need to do is heat it or evaporate the solution until the dry crystals are formed. And this process is known as crystallization, taking a solution and heating it up or just allowing it to evaporate until you form dry crystals, crystallization. And then we've got useful liquids from crude oil. So this is one that you've probably studied this quite a lot. How do you separate the different fractions in crude oil? Well, we use fractional distillation. Paper chromatography was used to separate a mixture of blue and red inks. So chromatography is a method for separating things in solution. A spot of the mixture was placed on chromatography paper as shown in figure 10. Give a reason why the start line is drawn in pencil rather than in ink. Well, we're trying to separate blue and red ink. So what would happen if if this line here was also ink? Well, that would also rise up the chromatography paper as well. The pencil line is great because it's insoluble in the solvent. So the way chromatography works is you have a solvent which rises up the chromatography paper, and it takes with it the mixture of inks, and blue and red inks are different chemicals, and they'll rise at different amounts. So the blue ink might get up to, say the blue one gets up to here, and the red one might get up to here. Now the pencil line just stays where it is, but if the pencil line was a ink line, then it would also move. The chromatography paper with the spot of mixture on it was placed in a beaker with the bottom of the paper in the solvent. On figure 11, complete the diagram showing the position of the chromatography paper with the spot of mixture at the start of the experiment. So the spot is going to be somewhere on the pencil line, like that. Here's the beaker, drawn in black, and the water is going to be up to around here. So the water is going to be up to here. The water, the solvent, must not be above the line. If it's above the line, all the stuff just gets mixed into the solution and doesn't actually work. Nothing will actually rise up. So the water has to be below the line like this. The chromatography was carried out, and the results is shown in figure 12. So here's the result. So here you can see it started here, and the red spot moved here, and the blue spot moved all the way here, and the water, which is the solvent, moved all the way up here. So the solvent always moves the furthest. The blue spot had moved 14.5 centimeters, and the solvent front had moved 15.3 centimeters. Calculate the RF value of the substance in the blue spot, giving your answer to two significant figures. Now it gives you the equation for this. So the RF value is just a number that we give to different chemicals in chromatography, and it actually allows us to compare those chemicals, and we can sort of figure out what chemical we've got from the RF value. But anyway, all we've got to do here is just use this equation. So we've got to stick in our values into this equation. We've got the distance travelled by the dye, 14.5, divided by the distance travelled by the solvent front, 15.3, and that's going to give us our RF value. So put that into the calculator, and we put that into the calculator, and we get 0.9477. Now, 0.9477 is not our answer, because the question has asked us to give our answer to two significant figures. So how many significant figures is this? Well, we don't count any zeros before the first number. So we don't count that. So we've got 1, 2, 3, 4. So that's 4 significant figures. We just want two significant figures. So we just want these guys here. However, if you're removing, so we've got 4 sig figs, and we're going to go down to 2, we need to consider this one here. Can you see how it's a 7? If that number is 5 or above, it means we round up. So this becomes 0.95 as our final answer, double underline, as for two significant figures. Because that third significant figure was a 7, we rounded up from 4 to 5, so 0.95. P, Q, R and S are mixtures of food colourings. There's P, Q, R and S. They are investigated using paper chromatography. Figure 13 shows a chromatogram. This is called a chromatogram at the end of the experiment. Which mixture contains an insoluble food colouring? So the reason chromatography works is because the substances we use are soluble in the solvent, therefore they rise up the chromatography paper. Can you see how Q has got one spot which has not risen up the chromatography paper? That must mean it contains an insoluble food colouring, because it hasn't risen up. If it's soluble, it would have risen up a little bit. So we can see that Q is the answer. Give a change that could be made to the experiment to obtain an RF value for the insoluble food colouring. Well, if we change the solvent, that's the stuff that comes up, solvent, sometimes water, if we changed it to something that the insoluble colouring was soluble in, then it would move up the chromatography paper, and we would get an RF value for it. Explain by reference to figure 13 which mixture is separated into the greatest number of soluble food colourings by this chromatography experiment. So we look in figure 13, we can see P has 3, Q has 4 dots, so 4 different colourings, S also has 4 dots. However, the question does say which mixture is separated into the greatest number of soluble food colourings. Now Q only has 3 soluble food colourings. It has 4 colourings, possibly, but 3 soluble ones, whereas S has 4, so S has the most soluble food colourings. A titration is to be carried out to find the concentration of a solution of sodium hydroxide. So a titration is a practical technique used to find out concentrations of an unknown solution, in this case sodium hydroxide. The sodium hydroxide solution is titrated with dilute sulfuric acid. The available apparatus includes a burette, a pipette, a funnel, a conical flask, and an indicator. State one safety precaution that must be taken when using sodium hydroxide solution and dilute sulfuric acid. Well, both of these things, sodium hydroxide and sulfuric acid, well, one of them is an alkali and the other one is acidic. Both of them are corrosive, that means they burn through stuff, so therefore we always use safety goggles. The mark scheme would also accept gloves, however, I have seen examples of questions where they don't accept gloves because goggles are the most relevant. Generally, the stuff we use in schools, sodium hydroxide and sulfuric acid, is not actually dangerous enough that you have to wear gloves. It's just going to sting a bit, whereas if it gets in your eye, even this dilute stuff, that is really very dangerous, so safety goggles are always a must. The sodium hydroxide solution is made by dissolving 4.3 grams of sodium hydroxide in water and making the solution up to 250 centimeters cubed with water. Calculate the concentration of solution in grams per dm cubed. So right now we have 4.3 grams per 250 cm cubed. So in every 250 cm cubed we have 4.3 grams. But we want to know how much grams we have in a dm cubed. How many grams per dm cubed? Well, 1 dm cubed is 1,000 cm cubed. So 1,000 cm cubed. So how many grams do you think are in there? Well, if there was 4.3 grams in 250, how many grams are there going to be in 1,000? Well, what's the multiplication? How many times bigger is 1,000 than 250? So hopefully you can see that is times by 4. It's 4 times bigger. If you times 250 by 4, you get 1,000. So how many more grams are there going to be? Well, it's going to be times by 4. So 4.3 times by 4 is, what's that, 16, 17 point. Now, there's actually a mistake in the specimen mark scheme. They've actually got an answer of 17.1. Now, there's no way you could actually get that. The answer is 17.2, definitely. Sometimes specimens do make mistakes like that. Now, over here we noticed that this was 4 times bigger. What if you just didn't see that? What if you didn't know it was 4 times bigger? Well, one way to do it is you should take the number 1,000 cm cubed, divide it by the number you had originally, 250, and that will give you what's called the scale factor, which is 4. So it tells you how many times it's been multiplied up. You then take the scale factor and multiply it by the grams, as we did over there, to work out your concentration. So this question asks you to write the balanced equation for the reaction of dilute sulfuric acid with sodium hydroxide. Okay, quite a nasty question really if you're not that good at doing equations. So basically we know it starts off with sulfuric acid, so we've got H2SO4. We've been given the formula for sodium hydroxide in other places, or you might just know it. It is plus sodium hydroxide NaOH. Okay, so that's our sulfuric acid plus sodium hydroxide. And then we draw a little arrow showing what it makes. Now this is a neutralization reaction because it's between an acid and a base. So neutralization reactions always make water, so H2O always, and a salt. So basically you take the bits which haven't been used to make the water. So you've got sodium, which is your positive ion, and sulfate, which is your negative ion. Now the sulfate, SO4, can you see how it's got 2 hydrogens? It means it's going to have a 2 negative charge, and sodium is in group 1, so it has a 1 positive charge. So to cancel out we need 2 sodiums, which means that we're going to have sodium Na2SO4. So that's our formula for the salt, and now we just need to balance it. So you can see how you've got 2 sodiums on the right hand side. I'll do a little line going down here. So you can see you've got sodium, we've got 2 over here, sodium, you've got 1 over here. So how can we make them the same? Well, if we put a big 2 here, now we've got 2 sodiums. Okay, now we need to check the oxygens and the hydrogens, all that makes sense. So we can see, let's do the oxygen. So for the oxygen, if we look over here, we got 4 oxygens here and 2 oxygens here, so 6 oxygens, and over on the right hand side we've only got 5 oxygens, 1 in the water and 2 in the sodium sulfate. So how can we get another oxygen? Well, if we put a big 2 here, we've now got 6 oxygens. And if we now count all the hydrogens, they should add up as well. Let's count, so you've got 4 here, 2 here, so 4, and we've got 4 here, so that all makes sense, so it's all balanced. This is a particularly nasty equation to write and to balance. This is sort of like the probably the most difficult question in the paper. Again, if you want more information on how to do this, I'm not going to go into it here because it's quite a big topic, but please look at my other videos and it's there. The results of titrations to determine how much of an acid is required to neutralize a given volume of alkaline are shown below in figure 14. So they did 4 titrations, and you can see every time the initial reading on the burette was around about sort of less than 5. That's where the burette started at, the volume started, and then it's the final where it ended up, and therefore this is the volume of acid calculated. So you just take one from the other, so 27 minus 0, 27.4 minus 2.1, and it gives you the volume of the acid used. So you can see generally the volume of the acid used was around 25, and this first one was a bit higher. So it goes on to say that 2 of the titrations in figure 14 should not be used to calculate the mean volume of acid required. Now, the reason we do more than one titration is because titrations can have inaccuracies, and if we do a number of different titrations, we can work out which 2 are sort of similar and which 2 are very different, and we just use the similar titrations, their values to do any calculations. So if you can easily see these values here, the titration 2 and titration 3, their values are very similar, whereas titration 1 is very much higher and titration 4 is a little bit higher. So therefore these 2 values, titration 4 and titration 1, should not be used to calculate the mean volume of acid required. So the reason they should not be used is because there are no other titrations which sort of coincide, which are the same. Now, there's a special word we use for when values are the same. We say concordant. So when results are within 0.1 of each other, like these guys are here, we say they are concordant results. Whereas this one over here is not concordant because it's not within 0.1 of anything. Now, there's another issue with this value over here. If you look at these values, they're only recorded to 2 significant figures, or 0 decimal places, where all of these values are recorded to 2 decimal places. So the titration 1 again would not be good because of the fact that it's not recorded to a greater required accuracy. So the number of significant figures is not recorded accurately enough. So our first 6 marker: describe the experimental procedure to carry out a titration to find the exact volume of sulfuric acid needed to neutralize 25.0 cm cubed of sodium hydroxide solution and obtain pure dry crystals of sodium sulfate. So 2 things. First, how do you carry out a titration? So this is just, you have to remember the steps of how you carry out a titration. And then the second bit is obtain pure dry crystals of sodium sulfate. Remember, all this stuff is in solution, so we've already talked about obtaining pure dry crystals, but again, you've got to put that down as well. So this question, you can see it's got the star. This is, you are being assessed on your quality of written communications. You're assessed on basically how well you're writing and communicating your answer. So is it logical? Are you using correct grammar, correct scientific language? So we rinse the pipette with the alkali, and the burette with the acid. So as we're putting the alkali, as it's the 25.0 cm cubed, that's what's going in the conical flask. We always put the exact amount of something. We use a pipette, and then we're adding the acid with the burette. That's what we're going to be measuring as our sort of titrate, how much acid it took to neutralize 25.0 cm cubed of sodium hydroxide. The reason we rinse the pipette with the alkali before we add the alkali into it is to remove any water or anything else, so that it's just alkali in the pipette. It makes it more accurate, the experiment. Same reason for the burette. The one thing we definitely don't rinse, though, we do not rinse the conical flask that we put the sodium hydroxide in with alkali, because if we did rinse it with alkali, we would have more alkali in there than we would want. We want only 25.0 cm cubed. Okay, next, using the pipette, we measure alkali using a pipette into a suitable container. Conical flask would be the most suitable. Beaker is not so good. I've seen questions before where they ask, why would you not use a beaker? Well, because a beaker, when you're swirling it, when you're doing a titration, you're swirling it, stuff splashes out a beaker, whereas a flask, this is specifically designed for this procedure, and the flask stops bits splashing out, therefore the experiment's more accurate. Okay, and you place the task on a white tile. The reason we use a white tile is so that you can easily see the colour change. Then we add a few drops of indicator. Now, because this is a strong acid with a strong alkali, a good indicator would either be methyl orange or phenyl phthalate. Next, we fill the burette with acid and a read volume of acid in the burette. Now, most people make the assumption that you have to fill it up to exactly 0.00. This is not the case. It doesn't matter where you fill the burette up to, as long as it's mostly filled, and then you record it accurately to 2 decimal points. So then we add acid from burette to the flask, slowly swirling the flask until the indicator just changes colour. So for phenyl phthalate, this is going to be sodium hydroxide will be pink, and as you drop the acid in, it will be making these colourless splashes, and the correct change is where it just starts to go colourless. It's more of a sort of faint, very faint pink, and you know that at that point they've completely neutralised each other, and you stop the titration and record. If you're using methyl orange, the colour change would be yellow to this sort of peachy orange colour. Okay, so you've got the correct colour change. You then read the volume of acid in the burette at the end of the titration, again to 2 decimal points. You then repeat the experiment until you get concordant results, so we're within 0.01 of each other. Sometimes this might mean repeating it just once, sometimes it might mean repeating it 10 times. You just do it until you get concordant results. And then, once we've got concordant results, we mix the same volume of alkali with the volume of acid determined from the titration, but we don't add indicator. So at this point here, we've completed the titration. So this bit here, that's our titration. We've done the titration. We're now trying to answer the next part of the question, which is how do we obtain pure dry crystals of sodium sulfate? Now to do that, we mix the same volume of alkali and acid determined from the titration, but we don't add the indicator. The reason we don't add the indicator is because we want it to be pure sodium sulfate, and the indicator would make it impure. Okay, so we now added the acid and the alkali in the exact concentration, so they've exactly neutralized each other, so therefore there will be no acid left, no alkali left, just the products, which is our salt, sodium sulfate, and water. If you remember the previous equation we worked out, those are the 2 products. And now we've got to get our dry crystals, so we pour solution into an evaporating basin and then heat the solution or leave the solution to evaporate until pure salt crystals are left. And finally we dry crystals using absorbent paper, or you can use a sort of drying oven there's a special chemical oven we can use as well. Now you'll notice that there are more than 6 points here. So let's have a look at how you're actually marked on this. I mean, you need to get 6 marks. You do need most of this here. But let's look at the mark scheme now. So the way the examiners mark it is they always start off at the bottom, and they read through your answer, and then they sort of look at the levels and see, have you reached level 1? You can only get to level 2 if you've completed everything in level 1. So in level 1, you have to demonstrate elements of chemical understanding, some which is inaccurate, understanding of scientific inquiry, techniques, and procedure, but the procedure lacks detail, presents a description which is not logical ordered and with significant gaps. So basically, if you gave us about a third of this So to get full marks, the way the examiners mark this is they start on level 1, they read through the descriptors, and then if you've got this, they move on to level 2 and then level 3. You cannot move on to level 2 until you've got everything in level 1. So basically, summing it up, level 1 is about a third of this answer with a few mistakes and not very logically ordered. Level 2 is just over half of this answer and relatively ordered in the correct way with maybe 1 or 2 mistakes. And then level 3, you need pretty much the whole of this answered in the correct order as it is presented, so logically ordered. So question 9 says, ionic compounds contain ions. Remember, ions are charged particles with a plus or minus charge. The number of electrons, neutrons and protons in 4 particles, W, X, Y and Z, are shown in figure 15. So we've got particles, different particles, and their number of electrons, neutrons and protons. Explain which particle, W, X, Y or Z, is a negative ion. Okay, so we need to know the charges. So electrons, what charge do you think electrons have? Electrons have a 1 negative charge. Oops. And we've got our protons that have positive charge and our neutrons which are neutral. So let's go through each of them and work out the charge. So you can see W has 9 electrons and 9 protons. So 9 negative charge, 9 positive charge gives an overall charge of 0, because remember neutrons are just 0, so they don't affect the charge at all. X has got 10 electrons, 12 protons. So you see you've got more protons, you've got 2 more protons, so it's going to have a 2 positive charge. So this one, 2 positive. And then Y's got 16 electrons and 16 protons, so again 0. That was also 0, that one there, W. And then Z, you've got 18 electrons and 16 protons, so you've got 2 more electrons, so it's going to be 2 negative. So a negative ion must have more electrons than protons, therefore Z is a 2 negative ion. So lithium fluoride is an ionic compound. So compound is 2 or more atoms chemically bonded together. It can be any sort of bond. In this case it's ionic. It contains lithium cations and fluoride anions. The electronic configuration of a lithium atom and a fluorine atom are shown in figure 16. So there's lithium, there's fluorine. Complete figure 17 to show the electron configuration and charges of the ions in lithium fluoride. So we know it's ionic bonding because it's called an ionic compound. We also know that because it's a metal and a non-metal. So we need to think what happens to the different atoms as they turn into ions. So who's going to, and remember in ionic bonding it's where people atoms lose or gain electrons to become ions. So who's going to lose, who's going to gain? Well, if you think about it, we can see that we want to have a full outer shell. So if lithium loses that one, then it has a full outer shell in its inner shell. So it loses this outer shell and it's very happy. And then fluorine wants to follow the octet rule. It wants 8 in its outer shell. It's got 7 right now. You can count them. So if it gained 1, it would therefore have 8 and be happy. So let's put those on. So we can see that lithium's got no electrons now in the outer shell, and fluorine had 7, has now got 8. So it's that gained 1. I could circle the one that it's gained. So this one here has come from over here, although don't write that in the exam. So the charge on this one, on this lithium, it's lost a negative electron. So if it's lost a 1 negative electron, it's going to have a 1 positive charge. So 1 positive. And this one here, the fluoride, has gained a negative electron, so it's going to have a 1 negative charge. So figure 18 shows the ability of different substances to conduct electricity. Explain these results by referring to the structure of the substances. So let's see what we've got. We've got solid calcium chloride. So that's calcium, which is a metal if you look in your periodic table, and chloride, which is a non-metal. So you probably think of what bonding it is. So it's probably going to be ionic bonding. And it's ionic bonding. Ionic compounds don't conduct electricity when they're in their solid state. Now we can see molten calcium chloride. Remember, molten is liquid, means liquid, so it's the same substance, ionic compound in its liquid state, and we can see it now conducts electricity. Again, that's evidence telling us that this is an ionic compound, that it doesn't conduct when solid and does conduct when liquid. Then we've got diamond. So remember, diamond is made out of carbon. It's one of the ones you should know. It's a giant covalent structure and does not conduct electricity. And then we've got zinc. So zinc is a metal. So again, a type of bonding we've got in there is metallic bonding. Metals have metallic bonding, and metals conduct electricity. So what's causing the different conductivity? Well, in liquid calcium chloride, the calcium and the chloride are free moving ions which are able to carry the charge. Diamond has no free moving ions or any free electrons, so is not able to carry the charge, and zinc has free electrons which are able to carry the charge. So going back to the molten calcium chloride, we can see we've got these free moving ions. So they're liquid, they're moving around, and therefore they're able to conduct electricity. So if you have free moving ions, then the substance is able to conduct electricity. If we look at the zinc structure, so zinc is a metallic bonding, so it forms this thing called a metallic lattice. It's a solid, so you've got a regular arrangement of the atoms, but the atoms actually in metallic bonding become ions. They lose their outermost electrons. In this case, zinc loses 2, each for each zinc atom, so it becomes a 2 positive ion. So we get the zinc ions get surrounded by these things called delocalized electrons. Delocalized just means they're free to do what they want, they're free to move around. So these delocalized electrons, often called a sea of delocalized electrons, are able to move around, and therefore they are able to carry a charge. So they can, therefore, if we put voltage through, they can carry a charge, therefore metals can conduct electricity. As I said before, if you look at the structure of diamond, however, it's got none of these free moving ions, none of these free electrons, so diamond cannot conduct electricity. Whereas there's another sort of allotrope, another form of carbon, which is actually called graphene, which is very similar to diamond, except the carbons only have 3 bonds rather than 4. And in graphene and graphite, there's actually a free electron. So they have a free electron, so they're able to carry, conduct electricity, much like a metal would. But diamond doesn't have that, so diamond cannot conduct electricity. So, looking at the mark scheme, what you need to say is that solid calcium chloride contains ions, which are charged particles. Solid calcium chloride does not conduct because charged particles are not free to move because they are held together by strong electrostatic forces. So in the solid, it does have charged ions, but they're not free to move, whereas the molten, they're free to move. So the molten calcium chloride solution conducts because ions are present which are charged and are free to move. Really important, they're free to move. The ions have separated and moved to electrodes of opposite charge. So the ions separate, the positive ions go to the negative electrode, the negative ions go to the positive electrode. Diamond does not conduct because it has a giant molecular covalent with no free electrons or no free ions. The outer electrons of carbon are used in bonding, and zinc metallic structure consists of delocalized free electrons which can move between layers of metal atoms, therefore carrying charge. So, similar to the last 6-mark question, basically if you get an explanation which links some knowledge, but a few mistakes, and it's not very clear, so you've sort of got maybe a couple of these sentences, then you can get 1 and 2 marks. If you've got about half of it, and it's generally well supported, you're up to 3 and 4. To get 5 and 6, you pretty much need all this information logically laid out as it is here. You saw me do some diagrams. Diagrams are good to do in the exam. If you do some decent diagrams, you can also gain marks from this based on your diagrams, as long as you include a written explanation as well. So this question is about solubility of different salts. This is just a memory task. You need to remember about the sort of solubility of chlorides and sulfates and carbonates. So most chlorides are soluble. There's a few exceptions, such as chlorine, bromine, iodine, but they're generally soluble. Most sulfates are soluble, and most carbonates are insoluble. In this question here, lead nitrate solution mixed with sodium sulfate solution forms lead sulfate as a precipitate. A precipitate is when two solutions or liquids or gases form a solid. So if you had a solid initially and another solid is formed, that is not a precipitate. A precipitate is, we only call it a precipitate if it's formed from solution or from gases. So in this example, we've got two solutions mixing together, forming a solid, so we call it a precipitate. In an experiment, the theoretical yield of lead sulfate, that's that one there, for the reaction was 2.85 grams. In the experiment, only 2.53 grams of lead sulfate is obtained, so less is obtained in the experiment than theoretically you should get. Calculate the percentage yield of lead sulfate in this experiment. So the theoretical yield is the sort of the stuff that you would get, the amount that you would get if the experiment went completely perfectly, the experiment went to completion, every single reactant reacted with the other reactant and nothing was lost. Now obviously this never happens, you never get 100% yield, because it's just that you always lose stuff, or the reaction doesn't go to completion, or perhaps you've got a few more extra of this particle, so therefore it won't fully react. If you had 10 extra of these ones compared to these ones, then they couldn't all react, so you never get 100% yield. But we can calculate what percentage we've got, so I'll give you the formula here. So the equation that you need to remember is percentage yield equals experimental yield divided by theoretical yield times by 100. So let's put the numbers in. So we've got the experimental yield, how much the experiment actually got, 2.53, divided by the theoretical yield, how much theoretically you should have got, 2.85, that was found there, times 100, throw it into a calculator, and this comes out to 88.8%. But watch out for these little sentences, these come up again and again, and they're such easy marks to lose if you don't spot it. Give your answer to two significant figures. So how many is that? Well, it's one significant figure, 2, 3. That's 3 significant figures. So we need to give it to just 2 significant figures. So 2 significant figures would just be those two there. But you can see how this is higher than a 5. Remember, if this is 5 or higher, we have to round. So we round up, so that turns that into a 9. So the answer is going to be 89%. Final answer. So this question is talking about the method used to make lead sulfate is you pour 100 cm cubed of lead nitrate solution into a beaker, add drops of sodium sulfate solution into a precipitate, remember that's the solid is seen, allow the precipitate to settle to the bottom of the beaker, pour off the liquid, use a spatula to transfer the solid lead sulfate onto a filter paper. And the question is asking you to explain 2 ways of improving this experimental method in order to increase the amount and quality of lead sulfate that could be obtained from 100 cm cubed of lead nitrate solution. So it's quite a nasty question. They do this quite a lot where they give you experimental procedures and ask you to improve. And unless you really understand what's going on, it's very difficult to suggest improvements. So let's just draw this out and see what's happening. So we've got a beaker, and in here we've got our lead nitrate, and then we're adding drops of sodium sulfate into a precipitate is seen. So we're getting some drops of sodium sulfate, there's the drops of sodium sulfate, and we're looking for a solid precipitate, and then we're allowing the precipitate to settle at the bottom and getting pouring off the excess liquid and getting a spatula to transfer this onto some filter paper to let it dry. So how can we improve this practical and so we get more lead sulfate? So if we want to get loads and loads of lead sulfate, why are we just adding a few drops of sodium sulfate? We want that sulfate to come along and react with the lead, take the lead. So by adding a few drops, that doesn't really make sense. So instead, let's add excess sodium sulfate. Excess means you keep adding it until you can't see any reaction take place. So there's a ton of that, and that will mean we get the maximum amount of lead sulfate. The next bit, which is a bit weird, is pour off the liquid. We never normally do this. If we're trying to get lead sulfate, we start pouring off the liquid. We're probably going to end up pouring some of our lead sulfate, which we just made, with it too. So rather, if we want to remove the liquid, what way can we remove a liquid from a solid, from the solid lead sulfate? Well, we can do filtration. So those are the two sort of obvious things that we could do. And those will get you both the marks. So it's sort of 1 mark for pointing it out, what's the problem. So in this one, the problem was we didn't have enough of the sodium sulfate. And this one, the problem was that pouring the liquid would lose some lead sulfate. And then give the way you can improve it. So in this way, we're adding excess sodium sulfate. In this one, we're using a filter. A couple other things you might think of. So another thing is we could purify the lead sulfates by washing it. So you wash the lead sulfate so the impurities are removed. And the other thing we could do again to improve the quality is drying it properly. So we could place the lead sulfate that we made in a chemical oven and allow it to dry, and that will increase the quality because it removes water, which is an impurity. Okay, so last part. So ammonium nitrate is produced from ammonia and nitric acid on a large scale in industry. Ammonium nitrate can also be made in the laboratory by titrating ammonia solution with dilute nitric acid. Ammonium nitrate crystals can then be obtained by evaporating off some of the water from the solution. Give 2 reasons why this laboratory method is not suitable for use on a large scale in industry. Well, if you think about a titration, so a titration uses a burette, which just looks something like this. The burettes don't get that big, so it wouldn't be very appropriate for the large scale because titrations just generally aren't for large scale manufacturing of products. They're just for testing things. So the volumes required of the solutions would be far too large for the titration or burette. So this laboratory method is also not suitable because we need large volumes of solution to be heated and then crystallized, and that's just not going to work using a titration method.